Good afternoon. This is your third digital class for the chapter Electrostatic Potential and Capacitance. Now in this class we are going to discuss few topics. The first topic which we are going to discuss is your electric potential at any point due to an electric dipole. Now in previous class we discussed what is dipole. Previous class in the sense in the first chapter itself we define dipole. Now dipole is your what? It is a system comprising two charge of different nature. One is your positive, another one is your negative, but their magnitude is identical. So see in this figure, you do have a dipole AB. Two charges, one is your minus Q, another one is your plus Q, and O is the center of the dipole. Now the distance from A to O is your L and B to O is your L. So you can consider the length of the dipole is your 2L. Now what we have to do, we have to define potential at P due to this dipole. So we are going to use the expression for the potential, and the expression for the potential is your V equal to KQ by R. So what we will do here, we will consider individual charges. One time is your minus Q, another time is your plus Q, and using that minus Q we will define the potential at P. Using plus Q we will define the potential at P. So the expression for the potential is your KQ by R. So here what we will do, potential at P due to minus Q is, this is your charge minus Q, potential at P. So distance is your R1. So formula is your V1 equal to minus KQ by R1. As Q is your negative, that's why we are considering negative sign. So potential at P due to plus Q. So is your V2 equal to KQ by R2. The distance from P to plus Q is your R2. Now we are going to apply superposition principle to define potential at P due to the system of charges. Here a system comprises two charge, one is your plus Q, another one is your minus Q. So potential at P due to this dipole AB is V equal to V1 plus V2. So V1 we have substitute minus KQ by R1 plus V2 is your KQ by R2. So you take the common part outside the bracket. So KQ is common. So here it should be 1 by R2 minus 1 by R1. Now our job is to define R2 and R1, and after finding R1 and R2 we will substitute it in the expression 3 to define potential V due to the dipole. So potential V is nothing but the potential at P due to this dipole. So practically the length of the dipole is very small. AB length is very small. So if AB length is very small, some changes will come. Now you see in this figure we have dropped perpendicular from plus Q to on the line OP. So BM is your perpendicular. So similarly we have extend this OP till N, and we have dropped a perpendicular from minus Q. So this construction part we have done to define R1 and R2. Now let me go for this figure under the note. Now is there any changes in these two figures? Just to try to observe it very carefully. Now you see here AB length and here AB length, the length of the dipole. So in this case the length of the dipole is more, in this case the length of the dipole is smaller. Now what changes will be here? If the length of the dipole is very small, then definitely here OM is very small compared to OM here, and ON is larger here and ON is smaller here. So we can approximate that if the length is very small, then you can consider that ON almost vanishes. ON almost vanishes. If ON almost vanishes, then AP becomes is your NP. Okay. Now you see these two figures. This is smaller figure, this is larger figure. Here the dipole length is very small, here the dipole length is very large. So if the dipole length is very small, what will happen basically? That this OM and ON part here is smaller compared to this figure. Here OM is larger, here OM is smaller, because the length AB is smaller compared to length AB in this figure. So practically dipole is very small. So if the dipole length is very small, then you can approximate AP as your NP, because ON is very smaller, and simultaneously you can approximate this one PB. PB is your pm. So let me consider this figure. Here, as the dipole length is very small, practically the length of the dipole is very small, so you can consider AP. AP is nothing but is your R1, so AP is nothing but is your NP, because if the length is very small, then ON is very small. So under that condition, you can approximate AP as your NP. So NP is your nothing but this. If you consider NP is your nothing but is your OP plus ON, ON plus OP. Now ON is your what? If this is your length L and this is your theta, then this ON is your L cos theta, and OP is your what? OP is your R. So similarly, as the length is very small, so you can approximate that R2 equal to BP equal to MP. Approximate MP, because the length of the dipole is very small. So MP is nothing but is your OP minus OM. So OP is your R and OM is your what? If you consider this is your L, then it becomes OM is your L cos theta. So R minus L cos theta. Have you understood? Only this part you have to understood. Others are very simple. So the explanation part is your what? As the length of the dipole is very small, that's why ON goes off, and ultimately AP is your nothing but is your NP. This you can compare with this two figure. As the length AB is smaller compared to this one, definitely ON value is less than ON value here. Similarly, OM value is less than here, less is here compared to OM. So if we make A and B very close to each other, you can approximate that ON vanishes, and if ON vanishes, then ultimately AP is your nothing but is your NP, and similarly BP is nothing but is your MP. So this approximation you have to understand. So we have got R1 is your R plus L cos theta and R2 is your R minus L cos theta. So if you substitute in this expression from 3 and 4, so 1 by R minus L cos theta, 1 by R plus L cos theta. If you take the LCM, R square minus L square cos theta, R plus L cos theta minus R plus L cos theta. So R goes off, it's your 2L cos theta by R square minus L square cos theta. So KQ2L cos theta. Now Q2L is your dipole moment we discussed in the previous class. So P K cos theta by R square. So this is the final expression for the potential at P due to this dipole AB. Now small p is your dipole moment. Don't confuse with the alphabetical P, this P and this P. This is your alphabetical P and this small p is your dipole moment. Already we have used this one in chapter 1. Now theta, you see in the figure theta. Now theta changes with the axial line as well as equatorial line. In axial line, theta goes to 0 because this P point comes to the axis, so theta goes to 0. So if you substitute theta equal to 0 at axial point, it comes out to be your pk by r square because cos 0 is 1. Now equatorial line, if you consider, this is your perpendicular bisector of the dipole, so theta is your pi by 2. So if you substitute theta equal to pi by 2, then V goes to 0. So at axial point, the potential due to dipole is your pk by r square, and at equatorial point it is your V equal to 0. So this topic is very important, and every alternate year or in consecutive year this used to come in exam, board exam basically. So only the approximation part you have to understand. Once you understand the approximation part, rest part is very simple. Only you have to substitute and you have to go for simple mathematics. So this is all about your electric potential at any point due to an electric dipole. Practically dipole is very smaller in length because polar molecule, you know, initially if you consider a neutral atom, center of gravity of positive and negative charge coincide, but if you apply electric field, the center of gravity of positive and negative charge separate and it becomes dipole. So atom itself is a very small small dimension, no? So dipole itself is a very smaller in length. So that's why one time we have approximate r is very greater than L. So for approximation this part neglected, and definitely if the length is very small, then this can be approximated. R1 equal to AP equal to NP and R2 equal to BP equal to MP. Okay, next topic we are going to discuss relation between electric field intensity and potential. So you see this figure, plus Q charge and A and B are two point within the field of this plus capital Q charge. So definitely if you want to bring a charge from infinity to closer to this charge plus capital Q, then definitely you must have to work more. Work more means more potential. So B has a higher potential, V plus dV, and A has a smaller potential, V only. So plus Q naught charge is here. So if I ask you to find the expression for the force, then the force expression will be your Q naught E vector. Force is repulsive force. This magnitude is higher, this magnitude is less. And work done to move the charge plus Q naught from this one A to B is your dW equal to F vector dot dr vector. So F vector equal to Q naught E vector dot dr vector. So it's your 180 degree. A to B is in opposite to F vector and E vector, so 180 degree. So you are getting minus Q naught E dr. So if you change the expression dW by Q naught, then it comes minus E dr. But potential already we have defined this work done per unit charge. So if you equate 2 and 3, the expression which you used to get dV equal to minus E dr, so E equal to minus dV by dr. Now dV by dr is called potential gradient because it changes with respect to the distance. So this expression can be stated as electric field intensity is equal to the negative of potential gradient. So if any physical quantity changes with distance, then we can define that one as a gradient. Now let us go for equipotential surface. The name specified equipotential means potential is identical. Now if we go for the expression for the potential, V equal to KQ by R. So what changes? Q and R. If Q is same and R is same, then the potential is identical. So you see the definition, a surface whose every point has same electric potential is called equipotential surface. How is it possible? If you consider a point charge, you can consider this circle as your equipotential surface because this concentric circle has a specific radius and the charge is your plus Q. So at every point on the circumference of this circle, the potential is identical. That's why these surfaces are known as equipotential surface. So for point charge, the equipotential surface is spherical. Equipotential surface surfaces for point charge. This is your spherical equipotential surface. Potential is identical. Similarly, if the electric field is uniform, then equipotential surface is your plane which is perpendicular to the field lines. So equipotential surface for uniform electric field. Uniform electric field means constant separation between the field lines. So this plane are the equipotential surface for uniform electric field. Sometime in exam it is asked, what is the nature of the equipotential surface for point charge? What is the nature of the equipotential surface for uniform electric field? So at that time you have to define. For uniform electric field, the equipotential surface is perpendicular to the field lines. Okay, more we'll discuss next class regarding equipotential surface characteristics part. Now let us go for this numerical. A potential difference of 50 volt is applied across two plates 2 mm apart. Calculate the magnitude of the electric field intensity between the plate. So here dV equal to 50 volt, dr equal to 2 mm, 2 into 10 to the power minus 3 meter. So we are going to use this expression E equal to minus dV dr. So if you substitute this one, we will get minus 2.5 into 10 to the power 4 volt. So you see, if it is the magnitude, then you only write the positive value. Don't consider the negative part. If it doesn't consider the magnitude, then you can write this one. Okay. So substitute the value for dV, that is your 50 volt, and dr is your 2 mm, 2 into 10 to the minus 3. So if you simplify this one, 25 into 10 to the power 3, so 10, so 2.5 into 10 to the power 4. So the magnitude is your, don't write this negative sign, 2.5 into 10 to the power 4 volt. Otherwise you can put the negative sign, it is not asked the magnitude. But in the question it is asked magnitude. So you can substitute 2.5 into 10 to the power 4 volt. So this is all about your electric potential due to a dipole, relation between electric field intensity and potential. So more we'll discuss next class. So go for this topic repeatedly so that things becomes clear. Thank you.